Hello, everyone. Welcome back to Codex. Today's speaker is Jamie Haddock from Harvey College. Dr. Haddock is an expert on mathematical data science, optimization, and applied convex geometry. Areas in which he's been recently active include randomized numerical linear algebra, combinatorial methods for convex optimization, tensor decomposition for topic modeling, network consensus and ranking problems, and community detection on graphs and hypergraphs. Today, she'll be telling us about randomized Kaczmarz models, corruption, consensus, and concentration. Take it away, Jamie.
Awesome. Thanks. Thanks, Mike. Thanks to all of the organizers for the kind invitation to this really great seminar. I had the pleasure of attending last week's with Stefan Steinerberger, which was really interesting. And it was kind of fun to see I think there's a wide variety of talks, but actually there'll be some cool connections to that talk. So, okay, so first, a little bit of a warning or an apology or something. So this talk, I'm going to talk actually about sort of three things, if I can fit it in. And so there's going to be these moments where I'll sort of pause really deliberately, and that's because I'm going to transition to a different topic. At any point, you should feel free to unmute and ask questions, but especially at those points, we'll be kind of really making a strong transition. So, so feel free to ask. Okay, so in this talk, I'm going to talk about the randomized Kaczmarz methods and their analysis. And I'm going to hopefully be able to show you some new applications and new ways to study and to apply these methods. I'm probably at this point preaching to the choir. I don't think I need to convince you that solving large-scale systems of linear equations is a really fundamental problem. We do it every day. If you have a computer sitting in front of you, which I hope you all do because you're currently seeing me through that computer, then you're solving linear systems, right? Computed tomography, anytime you get a CT scan, there's a inverse problem, which can be formulated as a linear system. But I'm going to talk a little bit today. I'm going to try to, I think, convince you that thinking about this problem is useful for other reasons. In particular, if we think about really simple methods for solving linear systems, we can take those really simple and well understood methods and generalize them to more difficult problems. They can give us actually really good intuition about how to solve problems that otherwise with kind of complex methods might be hard to approach. And additionally, one of the things I really love about these really simple methods is that they provide a model for analysis in seemingly quite different problem domains, which I'll also hopefully show you. Okay, so what are the Kaczmarz methods? The Kaczmarz methods are a simple family of iterative methods for solving consistent linear systems. So imagine you have some consistent system of equations. It's overdetermined, so there's many, many more rows than there are columns. Visualizing this pictorially, right, we have all of these hyperplanes, and we're hoping to identify the unique intersection of the hyperplanes. And the way that the Kaczmarz method iterates is in every iteration, we select one of the rows of our matrix A, which corresponds to one of our equations, which corresponds to one of our hyperplanes, and we orthogonally project the previous iterate xk onto that selected hyperplane, producing the new iterate xk plus 1. Okay. And the pseudocode or the formula for that orthogonal projection is given here. Okay, so you can already imagine this is a very generic family of methods. And specifically, I like to think about a randomized variant of this method, so the randomized Kaczmarz methods, which are exactly the same type of method. The only difference now is that I've specified the selection modality here. So when I'm going to select the row, I'm going to do so randomly. And specifically here, you can choose really any probability distribution over the rows and then try to analyze what happens. But really nice particular probability distribution is given here which is that every row should be selected with probability proportional to the square norm of the row. Okay. Okay, so, pictorially, we roll a strange, weighted M-sided die. Whatever edge comes up heads, I'm going to project onto that hyperplane. So, pictorially, maybe I first sample this row, and then I sample this row, right? And you can kind of imagine that as we move on, we're going to converge closer and closer to the solution. Okay, so I'm going to start by talking a little bit about a really elegant result from Thomas Stromer and Roman Vershinin, and this is actually 2009, that's a typo. So they showed that if the system of equations AX equals B is consistent, A is full rank, so there's a unique solution, and the rows are sampled according to this specified distribution, then the iterates converge linearly in expectation. Right, so on average, the error in the kth iteration squared is no larger than this constant 1 minus the minimum singular value of A squared over the Frobenius norm of A squared to the K times the initial error. Okay, so I like to think about this, just the errors are on average at least decreasing like a geometric sequence. This term 1 minus the minimum singular value squared of A over the Frobenius norm is less than 1. Okay, so yeah, I probably don't need a TLDR for this group, but just think the average ratio between the squared errors in sequential iterations is no more than this term, which is less than 1. Okay, and I can show you an outline of the proof in one slide, so I'm just going to go ahead and do it. It hinges on a couple of really simple observable facts. So the first one is that the picture here has a right triangle. So the Pythagorean theorem tells us that the error in the kth iteration is equal to the error squared in the k minus first iteration minus the distance that we updated, right? Which is, if we actually just bound that term, it comes from the update from that orthogonal projection. Okay, the second step is we're going to take a discrete conditional expectation. So conditioned on all of the samples made up until the kth iteration. So the only randomness right now is in that last kth iteration sample. That discrete expectation, the probability distributions are nice because the probability numerator cancels with the denominator here in this subtracted term. And then we end up summing over all of the squared entries of the residual. So we get the residual norm squared divided by that Frobenius norm squared. And then the last step is just to apply a residual bound. So a lower bound on the norm of the residual can be produced using the minimum singular value of A squared. And so we get that constant popping up. Okay, and the last thing to do here would just be to recurse. Okay, now I'm going to transition now into talking about noise and corruption. So remember, the Stromer and Vershinin result that I just presented to you assumes that the system is consistent, right? So AX equals B. In 2010, so just a year after the Stromer and Vershinin result, Deanna Needell showed that actually you can still say something about the randomized Kaczmarz method, even if the system that you're encountering isn't consistent. So if it's inconsistent. So for instance, if you're applying your system, your method to A, and then instead of having access to B, which forms a consistent system, you actually get something that looks like B plus E. So E is this little bit of like error or noise in the system measurements. Even in that case, we can say something pretty good. We can say that the randomized Kaczmarz method converges at least linearly in expectation, but up to a horizon term. So we call this the convergence horizon. And this convergence horizon scales with the maximum magnitude entry of the error, of the noise. Okay, so you can kind of imagine, right, just looking at this, that this is really meaningful as long as all of the entries of the noise vector E has relatively small magnitude. And if any one of the entries has a really large magnitude, that this result could cease to be meaningful almost immediately or immediately. Okay. So to summarize here, the randomized Kaczmarz method has good convergence properties in two cases, when we have well-conditioned and consistent systems, or if we have systems with small noise where this second term is relatively negligible, or at least won't really kick in until later on in the sequence of iterations. Okay. But what I want to consider is what happens in a different regime where the noise is not small magnitude, but we have something that I prefer to call corruptions, like you have some entries of your noise which are devastatingly large and would prevent the result of here from Deanna from being meaningful at all. Okay, so let me kind of give you a picture so you can see what I'm thinking about here. So here I'm imagining that we have a system, a very large system, and most of the equations are roughly consistent. Consistent, let's say for now, just like actually consistent. So there's some, large subsystem which is consistent, and then only a few entries or few rows here have been corrupted significantly, right? So our picture is like, many, many, many rows here, and then just a couple of rows living out here. And if I imagine running the randomized Kaczmarz method on this system, right, probably for a while, I'll be sampling good uncorrupted equations and making progress towards the solution. But anytime I sample one of these bad corrupted rows, I could undo, in this picture, nearly completely any of the progress that I've made. So the randomized Kaczmarz method will just fail on this type of a problem. Okay. So let me just get really specific. The problem I'm thinking about here is that I have a corrupted system of equations, which means that I have underlying the system, there's some consistent system here. B equals A times X star. It's overdetermined. X star is a unique solution to the system. And then I have just a fraction of entries that get corrupted, which causes the system to be inconsistent. Okay, now, to be specific, the fraction of corruptions that I'm going to allow in my right-hand side is beta. So no more than beta fraction can be corrupted. And the problem I'd like to solve is that given knowledge only of A and the corrupted measurements, I want to recover X star, the solution to the uncorrupted system. I want to say too, I'm presenting this problem. You should know that this problem has been thought of before. Really, if you think kind of deeply about this corrupted system problem, you might start to feel like it's connected to compressive sensing. In fact, some of the early compressive sensing literature looks at a problem that looks remarkably similar. So there are approaches for these methods coming from the error correction and compressive sensing literature, and they're often using either linear programming on L1 frameworks or just L1 minimization in general. And then there's also even iterative methods that work on the rows that are fairly simple, similar to the Kaczmarz method. Okay, so we're gonna talk about our own kind of approach to this method, which looks a little different. So I'm going to talk about two works. The first is joint work with Deanna Needell at UCLA, Elizaveta Rebrova at Princeton, and William Swartworth, who's now at CMU. And then I'll also briefly mention a second, more recent work, which is joint work with, again, Elizaveta Rebrova at Princeton and Anna Ma from UC Irvine. Okay, So I'm going to tell you about a method for solving corrupted systems of equations, but the idea is really simple. You should look at the residual to detect the suspicious candidate equations, like those that you think might be corrupted. Okay. So in principle, really, if you have a system with corruptions and you're sufficiently close to the solution, right? The magnitudes of the residual entries are related, are scaled copies of the distances to the hyperplanes. So if you're really close to the solution, your residual entries for uncorrupted equations will be relatively small, and your residual entries corresponding to corrupted equations will be relatively large. So if you're close to a solution, actually you can just read off who the corrupted equations are by looking at the magnitudes of the residual. And so in 2018, Deanna and I had this idea that actually we could exploit that fact to use simple, like vanilla randomized Kaczmarz, using kind of a like rerun procedure over and over again to try to detect the corruptions. And the idea would just be that if we ran, independent trials of randomized Kaczmarz enough, eventually we would end up kind of close to the solution of the uncorrupted system. And at that point, we could read off the corrupted entries. And so if we ran many independent trials, some of them would succeed and we would be able to see who those corruptions are. But the bad news is that independent trials, if you have even a relatively medium size fraction of corruptions, like 20%, then 1/5 of the individual steps you're taking, you can expect to be projecting onto corrupted equations, which can undo many, many good steps where you're selecting uncorrupted equations. So this approach that we developed using the vanilla randomized Kaczmarz method really could only handle very, very few corruptions. So then in 2020, with Needell, Rebrova, and Swartworth, we had what I think is a more interesting idea, which is to actually use the residual information in iteration to avoid taking any overly large and suspicious, possibly corrupted steps in each iteration. Okay. So the intuition here is super simple. If a sample that you've made implies a large step that looks corrupted, you just shouldn't take the step. You shouldn't project. Okay, so the method that we proposed is the quantile randomized Kaczmarz method, QRK. So again, kind of a dense slide, but what you should focus on is that there's really just kind of two steps here. We sample a row, and I'm using the uniform distribution, but you can use whatever probability distribution, makes your heart happy. You sample your row, and then you compare the magnitude of that entry of the residual to the magnitudes of all of the entries of the residual. If you're below a significant, if you are not too large, right? So if you're below a significant fraction of the magnitudes of the residual entries, then you will project, and otherwise you won't project. Okay, so I have this little schematic as an example. So here is our system. We have 3 uncorrupted equations passing through the solution given here in blue, and then 2 corrupted equations. Okay. Now, what I haven't mentioned is the quantile part. Really, this is a life lesson. Don't name your methods until you Google the definitions of the words that you're using. So really, I think that it would be easier to understand if we called this the Q percentile. So what I'm going to do is I'm going to ask whether my residual magnitude is less than the Q percentile of this list of magnitudes, and if so, project, and otherwise not. Okay, so here's my picture. I'm going to use Q equals 0.6. So I'm going to ask in every iteration whether the sampled row has residual entry less than the 60th percentile of all of the residual magnitudes. Okay, so in this picture, I'm sitting at x0, I sample this row J, and now I imagine forming all of the residual magnitudes. And for this purpose, let's just imagine that all of them are exactly equal to the distance to the hyperplane. So we've got very small distance, slightly larger distance, slightly larger distance, big distance, big distance, right? Those are in order. Okay, and the sampled row is actually the second smallest distance, second smallest magnitude. So it's less than the 60th percentile of the residual magnitude. So I make this projection. In the second iteration, okay, so now I'm sitting at x1, I sample this row, J, which corresponds to a corrupted equation. If I form, again, all of those residual magnitudes, right, I've got a couple of very small magnitudes. In fact, I've got one residual magnitude, which is 0. And then I've got a couple of large ones. J is one of those large ones. So it's above the 60th percentile of the residual magnitudes. So I just don't project. I stay still in that iteration, and x2 is the same as x1. Okay. All right. So we proposed this method in 2022, and in the same paper, we proved a convergence result. So we showed that if the matrix A is sufficiently incoherent and comes from a random matrix model, as long as it's large and tall, the fraction of corruptions beta is small. The Q, the quantile parameter, is chosen conservatively. Then the quantile randomized Kaczmarz method converges at least linearly in expectation to the solution of the uncorrupted system. So we can completely avoid the effects of the corrupted equations and solve the problem. Okay, so I'm not going to give you the full nitty-gritty details of the results, but what I want to highlight here is that one of the kind of disappointments of this result is that we had to lean on a random matrix model, which is, they're interesting, but they're not representative of problems that we would see in the real world. So not even a year later, Stefan Steinerberger came in and was able to generalize out our result and show convergence for any matrix as long as it's sufficiently tall and has well-conditioned submatrices. Okay. So the rest of the theorem is exactly the same. The QRK method, as long as beta, the fraction beta is small and the quantile Q is conservatively chosen, then the method, again, will converge to the solution of the uncorrupted system, at least linearly in expectation.
Hi, Jamie, you have a question in the chat on how do you compute the quantile? Can you do it without having to compute every single residual and sorting the list?
Awesome. Yeah, Zach, thanks for this question. This is actually going to kind of motivate one of the next things that I'll talk about. In principle, the way that we've described the method and the analysis technique that we've used thus far, we actually have to compute every single residual magnitude, sort the list, right, and calculate the, I should say too, I'm not an expert in quantile or percentile calculations. There might be some cleverer way, efficient way to do it. But modulo that, we still have the same, we're limited at looking at the entire residual. Okay, so one thing that I think is pretty cool is that the convergence rate that's given in actually both of these results is the same order as the standard randomized Kaczmarz method for the uncorrupted system. So it's kind of like, as long, other than just being able to completely throw out the corrupted equations and then solve that system directly, we're doing as well as you could expect. Okay, and then the second thing that I want to highlight is just that the corruption here is completely arbitrary. There's no statistical assumptions on the values of the corruption. In fact, all we assume is that the fraction of corruptions is sufficiently small. Other than that, the entries that you actually produce in the corruption can be chosen adversarially. adversarially. So, they could, for instance, try to form a small consistent system using those corrupted equations elsewhere to kind of confuse the method, but the method, as long as that fraction of equations is small enough, will not be fooled. Okay, so one thing I want to highlight, thanks to Zach for motivating this thought. Computing the entire residual in each iteration is often not possible. That's the whole reason why you would apply an iterative method. And in general, if you're computing a residual, you might as well be doing some other type of system solve. So this is far, far too costly. But the good news is that QRK provably works even when we just subsample the residual entries in each iteration. Okay, so the method doesn't change here much at all. All that's happening now is we're going to be sampling a fraction of residual entries to calculate the magnitudes of in addition in the method. Okay. Okay, so the summary here is that imagine that you take the quantile RK method and you change it so that rather than calculating the entire residual, it only calculates an alpha fraction of the entries of the residual. Then again, assuming some mild conditions on the relationships between that alpha fraction of the residual that you see, the quantile Q, and the fraction of corruptions beta, and some assumptions on the conditioning of the submatrices of A, then this subsampled variant of quantile RK will converge at least linearly in expectation. And the constant here, I'm hiding a bunch of ugly stuff that comes from the analysis, but this constant R is depends upon the conditioning of the system, your quantile Q, your fraction of corruptions beta, and the fraction of the residual UC alpha. Okay. Okay, and then in the last this last section here, I'm just going to show you quickly an experimental result. So here we're applying this subsampled QRK method to a corrupted system. What you're seeing is the iterate error squared versus wall clock time. So not iteration, but wall clock time. And so kind of as is expected, if you're subsampling the residual, so you're not calculating the full residual in every iteration, here blue is sampling about 15% of the residual, green is sampling 50% of the residual, and then red is normal QRK, which samples all of the residual. If you're sampling less of the residual, you're still able to see really consistent and fast convergence, but much, much faster because of that lowered in iteration time. Okay, so this is a moment where I'm going to transition kind of to a seemingly different topic. So if anyone has any questions, now would be a great time. Yeah, Mike.
So this algorithm where you're checking whether or not you should actually trust the step or take it or not based on whether or not the residual is disproportionately large. I was kind of wondering, like, have you experimented with only doing that check after, like, after some iterations? Because, like, I'm thinking that, like, if there's a big residual at first and your guess is random, that's maybe not so suspicious because your guess is random.
Yeah, I really haven't experimented with that. So there's a few things, like a few potential directions in kind of the same vein that I could imagine going, because you could also imagine that, like, early on, you start seeing like a single row have kind of consistently large residual, but it actually has really useful information. And so it'd be kind of interesting to try to develop variants of the method that, like, wait to do this thresholding until it kind of has a better indicator that like after sampling this row, there's changes in the residual that indicate it is a corruption. Like kind of doing, I don't know, I think of like a thermal method where they're like, okay, I'm going to increase the distrust on this row and decrease the trust. But yeah, I think that's a great idea. There's a lot of, I think, really interesting algorithmic directions there.
Cool.
Okay, well, feel free to interrupt me with questions, but I'm going to move on. So we've talked about corruption, which is I view as kind of a harder problem, but related to linear systems. And now I'm going to talk a little bit about a problem that comes from a different domain, specifically consensus. So the average consensus problem is like a toy or archetypal problem that's commonly studied in really a lot of areas in distributed computing in particular, but it's also really related to things that people think about in agent-based modeling and dynamical systems in general. The average consensus problem is you're given a graph. Okay, so graph. And all of the nodes in the graph have an initial like secret value associated to them that only they know. Okay. And the goal of the problem is that we want the nodes at the end of some process to all learn the average of all of the graph's initial secret values. But we want it to use only local graph communication. So what we don't want to have happen is that some node has to act as sort of like a main node and collect values from all of the other nodes. We want communication that only occurs over edges already present in the graph, and preferably that doesn't require passing information back and forth between nodes about, passing it like to the main node, for instance. Okay, so this is an example where I think talking about a couple of the applications of this problem makes it even more clear what the problem is. So my favorite example application of this problem is network clock synchronization, right? So you have a bunch of computers that are connected via some network, for instance, like a Wi-Fi network. All of the computers have their own, clock, their own internal sense of what time it is. And you don't want the computers on a single network to have drastically different, understandings of what time it is. That can make the communication packet sharing pretty problematic. And so what network systems often do is they'll have the clocks synchronize on the network. Okay, so like they should talk to one another as they're passing information back and forth and kind of agree, like, okay, you think it's a minute ahead of me, I think it's a minute behind, let's average. Okay, so there have been a lot of methods studied for this problem. It's a well-studied problem. One of the, I think, most popular and well-studied families of methods for this problem are called gossip methods, which are well-named. The way that they work is that over an iterative process, the nodes are allowed to gossip back and forth to one another about their secret values. Okay, so to make this specific, in each of the steps of this iterative process, an edge or edges are selected from the graph, and then the nodes that are connected by those edges update their held value to the average of the two values that were previously held along the edge. Okay, so we can see some examples of this. So for instance, here is a visualization of this graph after some steps of the gossip method, which highlighted these two kind of bolded edges here, the kind of left upper and right lower. So what happened was 84 and -17 got highlighted. They added together their values and took the average. The same thing happened with 60 and -9, right? So after those steps, this is the graph we're at. Okay, so I'm going to specifically talk right now about block gossip methods. So block gossip methods are just gossip methods where a block of edges are selected. So we select some set of edges from the graph, and then the nodes in each connected component of the induced subset of graph induced by these edges average their values. So that sounds dense. It just means forget about all of the edges that didn't get selected. Any of the graph remaining with those edges, all of the nodes that are now connected in that graph will average their grouped values. So it could be that 2 nodes are averaging values, but it could be like 3, 4, 5 nodes are averaging their values across larger connected components.
So wait, are nodes allowed to communicate here even if they're not directly adjacent, even if they're just in the same connected component?
Yes, yeah. So this does, thank you for that question, because this does kind of start to move away a little bit from that desired local communication. In some sense, we're kind of thinking that like every node could in principle talk to every other node, like in a computer network. And so if you induce like a path, let's say, that really maybe what you should do is just say like, actually the triangle should talk. Okay.
Okay, thanks.
For that.
Sorry, a little follow-up then. Is there some sort of thing we're regularizing against, or what prevents you from just saying everything's share right now and then we get the average value? Like what are we trying to balance against to prevent that being our way of just saying let's all gossip together at the same time?
Yeah, so I think to be honest, I don't have a great answer for that because I'm not like directly in the application areas. But I think in principle, the idea is that there would be some other, like this selection of edges is occurring according to some other iterative process. And then like alongside that, we're doing this averaging of the values, if that makes sense. So it could be like, you know, like in a computer network, 2 computers, like not every computer is passing information at all times. And so to introduce an edge that isn't actually needing to communicate just to average the clock time would be unnecessary and unwanted.
Thanks.
Yeah, thanks. These are good questions. Okay, so here are some examples. This is the first example I showed you. Here are the 2 edges, right? When we get the induced graph, it's just these 2 edges remaining, and the edges themselves are the induced subset. Okay, the induced subgraphs. We could also have, for instance, if the 2 edges that get activated are these 2, which connected -17 and 0.1, and then 0.1 and 1.9. When that path of 3, those nodes get activated, they are the induced subgraph. Those 3 nodes would average their value and become the number -5. Similarly, here, if we activate the triangle over those 3 nodes, the same thing happens, right? The induced subgraph contains the same set of nodes, and so this kind of gets at Mike's question. Okay, and this has been studied, these methods have been studied in the literature, so there is work that kind of considers these different forms of block gossip. So there's been work studying if the blocks that are selected in each iteration are paths, if they're cliques, if they're independent edge sets, which just means sets of edges that don't, no 2 edges share a single node in common. And so what I'm gonna say a little bit today is just about a mode of analyzing all of these methods, kind of, block ambivalent analysis of the block gossip methods. And this is joint work with Benjamin Jarman, who was a PhD student at UCLA and is now at GE Research, and Chen Yap, who was an undergraduate at UCLA and is now at Planet Labs. Okay, so get right to the punch. We proved in 2022 that if the graph G is connected, I'm going to let C0 represent, I'm going to vectorize the node values so that we can kind of think about the progression of the node values. So C0 is the initial node values. If we think then about the vector of values we're hoping to go to converge to, this is the C star, which takes the average of the C0 values and then just puts it in every entry. Okay, I'm going to visualize the sequential node values at every step of the randomized block gossip methods as, again, a vector denoted CK. And so what we showed is that as long as G is connected, then the randomized block gossip method, with some minor assumptions on the allowable blocks T, converges at least linearly in expectation, and the rate is controlled by this constant 1 minus alpha of T comma G. Okay, now let me tell you what alpha of T comma G is. So it depends upon 3 terms. The first was talked about a little bit in, well, a lot of it in Stefan Steinerberger's talk last week, the algebraic connectivity of the graph. The second is D, which is the number of blocks in the set T, so the size of T. And then R is the minimum redundancy, which is the minimum number of times that any one edge appears in a block set, or sorry, in the set of blocks. So if one edge, for instance, occurs in only one block, then this is R, that's 1. Okay, so it's kind of getting at, like, you know, bottlenecks in the information pass in the graph. Okay, so I'll just tell you what alpha TG is for 3 sets. So for path gossip, alpha TG is R, this minimum redundancy, times the algebraic connectivity, and then divided by 4 times the number of blocks. It's identical for the clique gossip case, which, you know, makes sense because if you have a path block, you could expand it out and get the exact same method with an equivalent, you know, filled out clique. For the independent edge set, we get an actually slightly different alpha TG. Here we get R times the algebraic connectivity, but divided by 2 times the number of blocks. So in principle, our result says, at least for this upper bound, that the independent edge set gossip method would have the best bound. Okay, so let me skip that. The way that we prove this is actually just by making a connection between the block gossip methods and the block Kaczmarz methods. So the block Kaczmarz methods are Kaczmarz methods where, rather than using a single row, we're using a block of rows. Okay, so select a block, sorry, this should be a subset, a block, which is a subset of the rows, that's tau. And then xk plus 1 is produced as the orthogonal projection of the previous iterate xk, but now onto the solution set of the subsystem indexed by tau. Okay, so in this picture, there's a lot of unnecessary stuff going on, but if we're, let's say our sample is this blue equation and this green equation, that's our tau. The solution set to that subsystem is this line, and so we orthogonally project our previous iterate onto the solution set of the 2 equations. Okay, and what we proved is kind of exactly what you probably are imagining. So if AX equals B is a consistent system, and we can relax the rank constraint, then under mild assumptions on the sampled blocks of A, the randomized block Kaczmarz method converges at least linearly in expectation to the solution that's nearest to X0. Okay, so this is a generalization of a result of Needell and Trop in 2014. We do several things. We relax the full column rank requirement on A that they have. We relax kind of an assumption about the block structure in the matrix. We force this result to depend on the minimum non-zero singular value of the matrix A rather than the absolute minimum singular value of A. And all of these things are really important for us to actually take this result and apply it in the average consensus Gaussian method, because the systems that we're solving in that case are not full rank, have a zero minimum singular value, and we don't want to have to form pavings of the subsystem. Okay, so the last thing I'm going to show you, I'm actually going to, I think I have to skip the concentration section. The last thing I'll show you is just an outline of the proof of how we use the randomized block Kaczmarz method for this problem. So the idea is to use the edge incidence matrix for the graph. Okay, so this matrix is indexed in the rows by edges and in the columns by nodes. The positioning of the 1 and -1 is arbitrary, but the non-zeros here indicate which two nodes are connected in this one edge. And then what we can notice is that if we set up a system which uses Q as our matrix and the vector of all zeros for our measurement vector, then this system using this matrix is demanding that all of the node values be equal across edges. Okay, so if it's a connected graph, that just means that all of the node values have to be equal to have a solution to this system. Okay, and randomized block Kaczmarz will converge to the solution of the system of equations closest to the initial iterative. So as long as we begin our randomized block Kaczmarz method with the initial secret values, will converge to that C star, that average value that we're seeking. Okay. So here we're just really kind of drawing this parallel. The samples on the graph correspond to samples in the matrix, and the methods then would be identical. All right, so with that, I'm going to skip forward to the conclusions. The randomized Kaczmarz methods are a really simple class of iterative methods. I really love this. I really love understanding mathematically these methods, in part because they allow us to take the methods and move them into other domains, either into domains with more challenging problems, or into domains where the problems are seemingly different, like in average consensus. Okay, so I'll just leave up here now some potential future questions. And thank you all, and I'm happy to take some questions if there are any.
Let's all smash the react button for our speaker.